Right now, a machine smaller than your fingernail is shaping almost every part of your day. It wakes your phone, it helps your car brake, it moves money through banks, keeps aircraft stable, and turns electricity into the images, messages, and answers on your screen. You almost never see it. But without it, much of the modern world would begin to fail. It is called a microchip. A microchip is not one tiny machine doing one tiny job. It is a dense network of electronic circuits built on a small piece of silicon. Some chips process information, some store it, some manage power, some sense light, motion, sound, pressure, or temperature. Together, they form the hidden infrastructure inside phones, cars, factories, hospitals, satellites, networks, and the hardware powering artificial intelligence. At the heart of this story is the transistor. The simplest way to imagine a transistor is as an electrical switch. A small voltage can decide whether current is allowed to flow or is blocked. One switch is not impressive, but billions of switches, connected in carefully designed patterns, can compare numbers, store data, render videos, or recognize faces. A chip does not understand music, maps, language, or games. It only controls electrical signals. And yet, that is enough. Think about an online mobile game. Your phone renders a three-dimensional world: light, shadows, sound, and animation. At the same time, it sends and receives data so other players can see the same world almost instantly. To you, it feels like one seamless experience. Underneath, every frame, every movement, every sound effect, and every network message is translated into enormous numbers of tiny electrical decisions. The game is software, but every instruction in that software eventually has to become a physical event inside a chip. Why silicon? Because it can be controlled. A conductor lets electricity flow easily. An insulator resists it. Silicon sits between those extremes. By adding carefully chosen impurities to tiny regions of silicon, and by applying controlled voltages, engineers can decide where current should flow and where it should stop. That controllability makes the transistor possible. And when transistors are combined, they create logic. Patterns that store ones and zeros, add numbers, move data, and coordinate billions of operations to the rhythm of an internal clock. A chip does not need one giant brain. It creates complex behavior by repeating simple decisions at unimaginable speed. And not every chip does the same kind of work. A central processor is built to follow general instructions. Graphics processors are designed to perform many similar calculations in parallel. Memory chips hold data so other chips can use it quickly. Sensor chips turn the real world into signals. Power management chips control how energy is delivered around a device. Different roles, different designs, but all of them rely on the same foundation, precisely controlling electricity. That control comes with a cost. Every calculation takes time. Every signal must travel through real physical connections. Every switch wastes a little energy as heat. That is why modern electronics have limits. A faster chip can deliver more performance, but it can also create more heat. And a powerful processor is only useful if it can be fed data quickly enough. Before a chip can run a game, guide a car, or answer a question, it has to be built. And that process begins with ultra-pure silicon. Silicon is formed into an almost perfect crystal, sliced into thin circular discs, and polished until the surface becomes extraordinarily smooth. These discs are called wafers. One wafer can eventually hold hundreds of copies of a chip design. But a wafer is still only a blank stage. The real challenge is building patterns so small
that no human hand could ever draw them. So chip factories use light. First, the wafer is coated with a light-sensitive material. Then, light passes through a blueprint called a mask or reticle and transfers its pattern onto the surface. It is like printing, but at a scale so small that the lines become the future pathways and switches of a chip. Then the wafer is changed. Some material is removed, other material is added. Tiny regions are altered so they conduct electricity differently. Metal connections are built above the transistors. Then the process repeats, again and again. Layer by layer, the factory builds a three-dimensional electronic city on a surface of silicon. This is why chip making is so difficult. A modern chip is not engraved once. It is built through hundreds of tightly controlled steps, often over many weeks. Every layer must align with the layer below it. A shift too small for your eye to see can make a circuit fail. A particle of contamination, harmless almost anywhere else, can ruin microscopic patterns on a wafer. That is why fabs are clean rooms. Their purpose is not simply to look clean. It is to protect structures so tiny that dust becomes a serious engineering problem. And even when the process is correct, not every die on a wafer will work. That is why testing and yield matter so much.
Eventually, the wafer contains repeated copies of the same design. It is tested, then cut into individual pieces called dies. Each working die is placed into a protective package. The package helps manage heat and creates the electrical connections that let the chip communicate with the rest of the device. Then it is tested again. Only after that can it leave the factory and become part of a phone, a Wi-Fi router, a medical scanner, a car, or a data center. The tiny black chip you see on a circuit board is not just silicon. It is the end result of chemistry, physics, precision machines, and testing. And chips do more than process information. Sensors let a machine detect the physical world. They turn light, motion, pressure, sound, or temperature into electrical signals that a chip can analyze. But chips can also drive action in the physical world. They send signals to actuators, motors, valves, brakes, robotic arms, and other components that create movement. The same microscopic switches that let a chip process data from a camera sensor can help adjust an aircraft's control surfaces in flight, trigger a car's anti-lock braking system, or guide a robot arm through a factory. A chip can receive information, make a decision, and send a command back into the real world, all in fractions of a second. Chips do not just observe the world. They help control it. And now, they're becoming even more important. Artificial intelligence is not invisible magic living somewhere in the cloud. Every chatbot answer, image generation, navigation route, streamed video, and online payment depends on physical hardware. Processors, memory, networking equipment, power systems, cooling systems, and data centers full of chips moving data and performing calculations. AI may feel like software, but software needs hardware. Hardware needs energy. And AI also needs data to move constantly between processors and memory. In many modern systems, moving information can be just as important as performing the calculation itself. That is why AI is not powered by one magical chip. It depends on entire systems, specialized processors, high-speed memory, network links, server racks, cooling equipment, and the electricity that keeps all of it alive. As these systems become more capable, the physical infrastructure beneath them becomes more important. The chips, the factories that make them, the servers that run them, and the grids that power them.
That is why a chip shortage can affect far more than phones and laptops. It can reach cars, hospitals, factories, logistics, energy systems, and the infrastructure behind everyday life. The tiny object inside your devices is not a small detail of modern civilization. It is one of its foundations. So the next time you unlock your phone, play a game, send a message, or ask an AI a question, remember what is happening beneath the glass. Billions of microscopic switches are turning on and off in a choreography designed by humans and written onto silicon with light. A microchip is not just a piece of technology. It is a hidden machine that turns electricity into the modern world.